In this video, I'm going to go through an applied optimization problem. The question here is you're at a campsite and you are lazy, so you want to do the minimum walking possible, but you have to get over to this tree where you've hung your food, and it's hung probably not high enough, but the idea is to avoid bears eating your food. And then on your way back, you want to fill up a pot of water by the river and then make it back to your camp. So you need to take some path between these 2 points that includes hitting the river somewhere. So many possible paths. You can wander around the tent and then hit the river and then wander around, but the fastest way to go would certainly be to take straight lines at least. And so we can eliminate a whole bunch of possible paths. So we should consider only paths, let's say, that go straight from the campsite to the river and then up to the tree and then back to the campsite. And so because this part of the trip is always going to be the same, we don't really need to include it in an optimization function or an objective function. So what we're really interested in here is knowing how can we best, in other words, shortest path, make it from the campsite to the river and up to the tree. And the path that I just showed you is clearly not a great one, because if I take these 2 paths to the river and back from the river to the tree, I can also just move a little bit closer, and the path from the campsite to the river will be shorter and the path to the tree will be shorter. So any points out here will be inefficient ones. Similarly, any points out here will be inefficient. So what we're really interested in is choosing a location along the river somewhere between the campsite, in other words, directly below, or in a perpendicular line from the campsite to the river, from here all the way out to a point sort of below the tree location. And so that's the variability in the problem. So what we've done, just by thinking about possible paths, if we've identified a single variable that we can change, which is location on the river. Now, it's also possible to express this all in terms of, let's say, the angle here, theta, where theta could vary from 0 all the way up to whatever the angle is in the case where we have a triangle 100 on this side and 300 on this side. But angles are trickier to work with, and they would probably involve trig functions, so we can probably avoid dealing with trig functions by not choosing the angle description. So I'm going to choose instead to pick a point, and I'm going to pick it at random. So this is supposed to represent some arbitrary point, and I'm going to call that location x. I'm going to call this location 0. So this is x equals 0. This is some arbitrary choice x, and we can go all the way up to 300 meters. Now I'm going to choose to measure in units of hundreds of meters here, so that I can just use 3 instead of 300 up here, for example. Okay, so now the choice is to make the point where we fill up our water at x, and then we're going to move straight to x, and then from x straight up to the tree. And now we have to find the sum of these 2 distances that's minimum. So in other words, we'll move that point x around and find the shortest overall distance. So let me write down what that distance function looks like. Oh, before that, so I like to do a little bit of exploring before I start working on a problem, so I can figure out what I anticipate to be the nature of the solution. So for example, in this case, first I would look for extreme cases on the interval, the domain for the function. So it looks like my domain goes from 0 to 3 here, because those are the possible x values I'm interested in. So what would it mean to choose an x value of 0, which is at one far end of my x interval? That would mean that I go straight down to the river, and I get my water, and then I go up to the tree. So the question is, if I do that, is that possibly going to be a minimum, or do I expect the minimum to be at the other end? Or possibly somewhere in between. So this one I would call an interior minimum, and if the minimum ended up at the endpoints, those would be endpoint minimums. And that distinction isn't too important, but if you can get some intuition for whether you expect to be on the edges here or somewhere in the middle, that's helpful in checking your results at the end. So it's actually a little bit subtle to figure that out just by looking, but my instinct is to say that our minimum should be somewhere in the middle. And we'll see if that works out. Okay, so the distance I'm going to call, let's draw these in. I have two distances here. This one is part of a triangle with a right angle here. And the distance down on this side is x. And the distance here, I'm going to measure in units of hundreds of meters, so I'm going to call this 1. And then that means that the hypotenuse is going to be the square root of 1 plus x squared. Similarly, on this side, I have a distance here, and I could calculate it right away as 3 minus x, but I'm going to call it y for now. It's just a different distance in the problem, and that will have a hypotenuse here of, let's see, so we have a side here of 2, and here y, so we're going to have 4 plus y squared. Now the reason I'm doing that is because my total distance, I can express it in terms of an x and a y, and that'll be the length of the first path, or the first straight line I walk, plus the length of the second. And the reason I do this is because it's a little bit too simple for it to seem like a constrained optimization problem, but really we know that x plus y has to be 300, so we actually do have a constraint in here. So now I can, follow that strategy that I laid out in the previous video, or one of the previous videos, and use this constraint, solve for y, and then plug that into our objective function, which is the function that we're trying to maximize. That's what the objective function is defined as. And so what we end up with here is d of x 3 minus x, and I'm going to call that h of x, just to give a new name to the function so that I can think of it as a single variable function now, and not get confused when I start taking derivatives with respect to x, because I don't know if it's derivative with respect to this entry here, x, or all the x's that appear in it. So I'm going to just remove any of that ambiguity and use the function name h of x for the one with 3 minus x plugged in for y. Okay, so I get a 1 plus x squared here, plus the square root of 4 plus 3 minus x squared here. Okay. So what we're interested in is finding the minimum of this function. And because we're on that finite domain, remember when I suggested that we test points out here, we found that as we bring the point that we go fill up the pot with water closer to the one directly down towards the river, we found that the total path decreased. So I'm actually now thinking that it's most likely that that decrease will continue right across here, similarly across here, and these are going to end up being maxima, or high points locally at least, and so they're probably not going to be that relevant, but let's calculate them anyway. So we have h of 0 is going to be, the square root of 1 is just 1, and here at 0 we have, on this one we have 3 minus 0, so this is square root of 4 plus 3 squared is 9, so this is 1 plus root 13. All right, so that is one of them, and then if we evaluate this at 3 at the far end, we get square root of 10 plus, now here we have a plugging in a 3, and here we get 3 minus 3, so that's 0, so then it's just square root of 4, which is 2. Okay, so these are our two endpoint values. Now let's see if we have a critical point in between, or maybe more than one. I'm expecting only one. So we have a derivative to take now. So we take h prime of x, and so let's see. So we're going to get, when I have a square root, that means I have a power half, and I'm going to get a half coming down, so I'll put a 2 in the denominator, and then when I bring the power down, it becomes minus a half in the power. So now I have the square root function down here. But then there's a chain rule because there's something underneath the square root other than x, and the derivative of that function there is just going to be 2 times x. And then I add to that. And now same thing happens here. We have a 2 down in the denominator from the half that came out of the power. And then we're going to just have the square root function because it's now to the minus half, so it goes into the denominator, that minus sign. 3 minus x squared. And now by the chain rule, we have to take a derivative of this guy. Now there is a complicated chain rule structure here. We have to take the derivative of what's underneath the square root. The 4 becomes a 0 when you take the derivative, and then the 3 minus x all squared is 3 minus x with a 2 out in front. You bring the power down in front. But now this is x squared with 3 minus x plugged in. So I have yet another chain rule. I have to multiply this by minus 1, which is the derivative of 3 minus x. Okay, so there's some cancellation. I can cancel the 2 on top and bottom in both of these. And I'm going to bring this minus 1 out in front and erase this plus and to make it a minus, and that means I can get rid of this minus 1. And now I want critical points, so I'm going to set this equal to 0. All right, so that's equal to 0 when x over the square root of 1 plus x squared, square root of 1 plus x squared is equal to 3 minus x over square root of 4 plus 3 minus x squared. Now I've got x's in the numerator and denominator, so I'd like to clear all of those out. So I'm going to multiply by the denominators on both sides. So on this side, when I multiply by both denominators, I get cancellation between these ones, and I'm left with x times the square root of 4 plus 3 minus x all squared. And on the other side, that's too close, hold on. On the other side, I get 3 minus x multiplied by the square root of 1 plus x squared. So here I've multiplied both sides by both of these square roots. This is the 1 plus x squared, and then the 4 plus. All right, so clearly I have a product of things with square roots. If I just square both sides here, I will get rid of those square roots, and then I'll be left with, let's see, it's going to be a quadratic multiplied by a quadratic. So it's going to be a fourth order polynomial on both sides, but it looks like there will be some cancellation. So let's just do that. And one thing to look out for is when you have an equation and you square both sides, you get a new equation that's not quite equivalent to the first equation, because once I square it, if the two sides are equal after squaring, they may not have been equal before squaring. In other words, this might, when I finally get my x value, this might come out to, let's say, minus 3, and this might come out to 3, and they're not equal in the original equation, but once I've squared it, they become equal. So I might get some extra roots, and we have to look out for that. All right, so squaring both sides, I'm going to get x squared, 4 plus 3 minus x squared, and that's equal to 3 minus x squared times 1 plus x squared. Okay, so you'll notice that I have an x squared multiplied by a 3 minus x all squared. And here I have an x squared multiplied by a 3 minus x all squared. They have the same sign in front of them, and they're both on either side of the equal sign. So I can cancel those two out by subtracting them from both sides without even multiplying through. So I'm just going to cancel this part of it here and this part of it here. So what I'm left with on the right-hand side, on the left-hand side is 4x squared. And on the right-hand side, I'm left with 3. Well, let's square that out. Let's multiply that through. So I get 9 minus 6x plus x squared. So now bringing all the terms over to one side, I'll get a quadratic. And I get 3x squared plus 6x minus 9 equal 0. There's a common 3 that I can divide through by. So I get x squared plus 2x minus 3 equals 0. And I can factor this into x plus 3, x minus 1. Because you can see I get minus 3 from the product of these two. And to get the 2x, I get that by multiplying a 3 times x and a minus 1 times x gives me 2x. And then finally the x squared. So what we now have is this squared version of the equation here has solutions x equal minus 3 and x equal 1. Now, it seems a little bit strange if you think about this, and this is really an important step. I encourage you to always, once you get an answer, go back and check to see if it fits with your intuition for what's going on in the problem. Here we have at x equal 1, which is actually not too far from where I drew this point, coincidentally. And so that kind of makes sense. We get an interior critical point. But what about this one? X equal minus 3. That's way down here. And there it seems a little bit odd that I would get a critical point because it seems like the further off to the left I go, the longer that path is going to keep on getting because both paths from campsite to river and river to tree are both increasing. So this is a very strange one. So I'm actually just going to go back and double check to make sure that nothing weird happened. And this is really what I was talking about when I mentioned that squaring this equation can introduce extra solutions. So if I plug in a minus 3, I'm just going to do this over here. So here x equal minus 3 as a check. Here I'm going to get minus 3 times the square root of 4 plus 6 squared. That's this expression with minus 3 plugged in, which is minus 3 root 40. I can bring a 4 out of there, and that becomes 2 on the outside, so I get minus 6 times square root of 10. And then on the other side, I have 6 multiplied by square root of 1 plus x squared, which is 10. So I get 6 root 10. So on one side I get minus 6 root 10. On the other side I get 6 root 10. These are not equal, but because I squared both sides of the equation, I end up introducing x equal minus 3 as an extraneous root. So this one is not really a root, and there is my critical point. And now I need to figure out if, well, actually, I don't need to figure out anything here because we have, what I was going to say is I have to figure out if this is a min or a max. And because I'm on a bounded closed interval and it's differentiable everywhere in that interval, and I have calculated the value of the function at the endpoints, all I have left to do is figure out the value of the function at the critical point, and if it happens to be higher than the endpoint values, it is the max, and if it happens to be lower, it is the min. And the reason for that is, I mean, there's a theorem that tells us that, but just intuitively, if we start off at one end with a value of, on our interval, let's say this is 0 to 3, and we have a value of 1 plus root 13 over here, and a value of 2 plus, well, that should be a little bit higher, 2 plus root 10 over here, and we find that our critical point is down here. If it's not a min, if it's not a min, then I have to somehow go lower before coming back up, either to this side or maybe to the other side. But if I did that, I would have to have a critical point somewhere between where I'm at this one and the endpoint, because I can't turn around on a smooth function without having a critical point. And we didn't find any other critical points. So what that means is that all we have to do now is we evaluate h of 1, and that will give us a value either bigger or less than the endpoints, and that'll give us our minimum. So h of 1 is going to be the square root of 1 plus 1 squared, which is just 2, plus square root of 4 plus, and then 3 minus 1 is 2 all squared is 4. So this is equal to the square root of 2 plus the square root of 8. Now 8 is 4 times 2, so I can bring a 2 out, so it's 2 root 2. And that is 3 times root 2. So now we're stuck with comparing three different numbers, each of which has a square root in it. But we can still do this. Now, obviously, you can do this with a calculator if you have a calculator. But if you don't have a calculator, how do you do this? Well, so square root of 2 is about 1.4. So 3 times 1.4, certainly less than 1.5. So 3 times that is about 4.5. And that's a little bit bigger. That's on the big side of what it actually is. And then h of 3 is the easier one here. H of 3, the square root of 10 is slightly bigger than 3. So this is on the big side here. So the square root of 10 is slightly bigger than 3, so I'm going to make it smaller and call it 3. And then add 2, that's 5. So that's on the small side of what it actually is. That's smaller than what it is. And so we have number 5 is smaller than h of 3, but already still bigger than h of 1. So we know that h of 3 is not a min for sure, because h of 1 is bigger than it. Sorry, is smaller than it. And what about h of 0? H of 0, well, 13. 13 is somewhere between 3 and 4, and add 1 to that, and we get somewhere between 4 and 5. So that doesn't really narrow it down that much for us. But because 13 is somewhere between 3 and 4, I'm just going to take a wild stab in the middle and say, what is 3.5 squared? Is that bigger or less than 13? So if I square 3.5, I get 5 times 5 is 5. Carry a 2. 3 times 5, 15, 17. And then a 0, 3, 15, 1, 3, 9, 10. So adding those up, I get 5, 2, 2, 1. So 2 decimal places, so it's 12.25. So 3.5 squared is 12.25. And we have square root of 13, which is going to be bigger than 12.25. So then the square root of 12.25, which is 3.5. So this one here is definitely bigger than 1 plus 3.5. So it's bigger than 4.5. And so h of 1 is clearly our minimum. Okay, so I will wrap that up here with the conclusion that we should get our water 100 meters upriver from the tent.